So BH curves in magnetism, very common topic, and we need to get into the topic of BH curves because unfortunately the permeability is not always constant. It's not constant for a material. The permeability actually depends on the flux density, but the flux density depends on permeability. So magnetic circuits get complicated in that it's not a constant material that sits there as a magnet sitting on your desk in real equipment. So in a motor or in a transformer, these cores, these parts that are magnetized, are actually become magnetized, demagnetized, magnetized, demagnetized, depending on things like, the AC current being fed to them. The primary current of a transformer and the secondary current of the transformer, it being under load condition or not, it being initially started up, and then you have this high influx current. All of these things happen in a real life magnetic circuit that is part of electric machinery that make it so that permeability is not just one number. Not one number. It is actually a curve. It's actually a relationship. So we have to know how this relationship works. So we have to first know this equation, which we do, and we've had videos on that, what this equation is. We know what flux density is. We know that what the magnetic field strength means. It's magnetomotive force divided, normalized by the length of that magnetic material. And we know what permeability means. And just reminding you that permeability means how much this core permits magnetic field strength to be established in it. How happy it is to make lines of flux and become magnetized. So highly permeable says, yes, I love to become a magnet. And low permeability means, no, I don't magnetize very well, choose a different material. All right. So we know all of these things. So now if we look at it, if we rearrange this equation into this format, we see that it's magnetic field strength over it's flux density over the magnetic field strength, and those interrelate. And if we look at this from just a math point of view, we commonly say rise over run. And from just a math point of view, not a physics point of view, rise over run means slope. So now we're going to get a little bit mathy about this electrical machines topic, and we're going to look at what does the math tell us. So we know we're in this real weird word where magnetic field strength is going to vary and flux density is going to vary. Sorry, permeability is going to vary, flux density is going to vary, magnetic field strength is going to vary, and we're all very upset about that. It is then going to be material specific. We need to see the rise over run of this. And the way we do that is actually on this curve. So this curve now relates the material that we want to look at. So let's see if I can erase a little bit of my scribbles on here. Whoa, that didn't do it. And they won't go away. So I have some old-fashioned material on here that won't go away, but that's okay. It's good stuff. Okay, so let's look at it from now. And let's make sense of this curve, because it's really important when we get into electric machines, transformers, etc., that we know what's going on in this curve. Let's start with the axes. Along the x-axis, we have magnetic field strength, which is H. And H, if we remember, it's the magnetic field, it's the force of that magnetic field over the length of that magnetic field. So it's like, let's say this is a transformer core that looks like this, and we have some windings, and we have some windings, and we have some windings. Well, then the mean path length goes in the middle there, and we're looking at how much magnetic force there is per this unit length. So a little tiny bit of this geometry is going to be either strong or weak. Okay, so we're normalizing it so we can compare it to like a tiny circuit, and we're comparing how strong that material is per unit length. Okay, that's what H is. We should know what that is. Look at the other videos if you don't know. Now, on the y-axis, we have flux density. If you remember what flux density is, well, flux is just those lines of those magnetic field lines that go through a material. And if there's a lot of magnetic field lines in that material, I can cut a cross section of this material and I can say, whoa, I'm going to picture them like an arrow, like a arrow going through the page. They hit the page and then they go all the way through, and there's the little crosshatch from those feathers at the back of the arrow. Okay. So look at how many lines of flux we're going through there. Well, let's take another material. It's a density, which is also a normalized, right? It's normalized. And if I take the same shape, normalized by the same cross-sectional area, or any cross-sectional area, now I have more lines of flux coming through. Look at all those lines of flux going through. They went through the page because I cut a cross-section, and the cross-section's right here that I cut. And so this one has higher flux density. It is just the density, is the number of arrows that are shooting through there, it's the number of flux lines that are shooting through there. So we would expect this one to be more magnetized. So as we go up, we have more magnetized, more magnet stuff. I'm going to say more magnetic. And as we go higher on this axis, we say it's more magnetic because it's more strength of that magnetic field. So we're kind of happy if we kind of, my arms are going out and up. We want to be, way over here on this curve in order, to be like in a good magnetic state. Now, so those are the axes. Now, the next thing you have to know about this BH curve is that steel, like every material, it's material specific. So back in the day when we were, simplifying magnetics, we said, oh, the permeability of steel is always this. Oh, the permeability of iron is always this. Permeability of air is always mu naught. And everything was pretty simple and easy, and we were pretty happy. But now we know that it's actually material specific, and it relates to a curve. So here are the curves. Steel actually behaves like this, iron behaves like this, air behaves like this. Now let's take a look at one of these curves. What happens on one of these curves, if I can go and highlight it, I'm going to highlight steel because we like steel. What we often do. Yeah. What we often, it's going to be a great video. What we often do. Okay. I'm going to highlight one of these. What we often do is we make a core that is very useful to us, and we make it out of strips of steel with laminations in between. We do that to reduce eddy currents. Eddy currents give us a lot of losses. Eddy currents are they get transferred into heat, and we don't want heat. So I'm going to highlight this steel one. What's happening is, as I get some magnetic field strength, remember magnetic field strength comes from current times the number of turns. It's the current in one turn of one of these winds here, times the number of turns of this wind. So as I turn on the current, then I'm going to get more of this force per unit length. And as I get more of this force per unit length down here, then I'm going to get some of these, flux lines established. And then as I get more force per unit length, more flux lines are going to establish. So I kind of go from this situation to this situation of a low flux density to a higher flux density. So look at me climb up this flux density curve. And steel actually has this property that per unit of magnetic field strength increasing, there's actually an equal amount of flux density increasing measured in Teslas. And look, so that means it's linear. And what I have on this curve here is rise over run is linear. Now, where did I talk about rise over run? Well, I just said in this very video that permeability, the amount of happiness a circuit has to establish magnetic flux, is rise over run. Permeability is rise over run. It is, at this point, 1,000 over 1.2. It's H over B. It is 1,000 over 1.2 amp turns per meter over a Tesla. And you have to break Tesla into its base SI units. I'm not a big fan of the unit Tesla because it's not in base SI units. Anyway, that's not for this video. We should know how to convert those and then get to the appropriate units for permeability. So, but here we have it. We have a nice rise over run here. And it was linear. So we can say that the permeability of steel is rise over run right here. Great. It's going to be a certain value. Now, what starts to happen is now as I go more current, of course, we don't change our windings. We don't as we're using our transformer, take it back to the factory and wind some more things on it as it's working. That's kind of silly. We just increase the current more. So now let's get another color. Now we're going to sit here. Now I'm increasing it more into like this 2,000 to 3,000 range because I increase this current, because I'm just going to give it an AC signal and alternating current goes up, 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 up. So we're going up, 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 up. Now we have 3,000 for H. Great. And you know what? Flux density doesn't keep up as much. Flux density says, oh, you know what? I'm not going to be linear. I'm not matching you anymore. I'm not matching your energy. So I'm not rising as much for your running. So magnetic field strength is still running along this x-axis and your flux density is no longer catching up. Why is it no longer catching up? Has to do with the physics. Because you have already aligned most of the material that is inside each grain, that is in between each grain boundary. You have almost established all of those grain boundaries, and you have almost moved all of those particles into a north-south aligned direction. They have almost all aligned together. They haven't all aligned together, but they have almost all aligned together. And if I draw a little diagram of what I'm talking about, which you know from another video, you know this, is that, you know, these little north-south used to be like this, but when they got magnetized, they got all excited and they went in one direction. And now they all sit like this. Cool. This is a magnetized material. And I went, the relationship was linear as I went and magnetized north, south, north, south. And these are all lined up now, and I'm a pretty happy magnet. But what's happening right now at this part of the slope is that, you know, there's still a couple that are hard to turn. Okay. Still a couple that are hard to turn. And then once, okay, so this is the blue part of the curve. The blue part of this curve is kind of in here, okay? And the green part of this curve is where they were really working together to turn those north-south little mini magnets together, all right? And I'm not talking very technically here. I'm not talking about the physics of it. Now, we're getting pretty happy, but then something dramatic happens. Then the drama happens on this curve. The drama happens on this part. It looks like this in the material. It looks like this. We've already, I stopped drawing it because I got so excited about this nice little diagram. Now I've already turned these all north-south because H was trucking along and magnetic field strength was trying to catch up. But then by the time we get to this pink zone, H is still trucking along. H is still trucking along because I'm giving it more and more current. But you know what? This is not responding anymore. So there's no more flux density. There's no more lines of flux being established. It's like I've checked out. I am fully magnetic. I'm not going to get any more magnetic. So here I am as magnetic as possible. And you did your job down here. You might as well not give it any more current, because you're not going to get any more magnetized, because you can't get any more magnetized because they're already all aligned to north-south. You can't magnetize steel more than its ability to get magnetized. It's a physical thing. That's what the BH curve tells you. Now, your question is, what is permeability? Good question. Is the permeability rise over run over here? Sure. Rise over run, pretty close to 0. That was a bad way to write 0 because it looks like the symbol for flux. Is not rising very much, right? I'm going to say nil. So I'd say that's a bad place to measure permeability. Is it a good idea to measure permeability here in the straight section? Yeah. Is it a good idea to measure permeability here? What would it be? It would be the tangent to this line. Now we're getting all mathy again. Rise over run as a tangent. Well, then, you know, you can easily pull this tangent of rise over run. Rise is now 2000, and run is 1.8 minus 1.2. That would be rise over run, right? Rise over run, easy to calculate. Do I want to calculate it here? Probably not. That would be close to 0. Do I want to calculate it? Do I want to take a straight line from here to here? That's a good way to calculate it. What's the rise over run here? Well, the rise would be like 1.5 minus 1.2 is the rise. And I hope everybody knows what I mean by rise over run. It's y, it's delta y over delta x. So And, I'm talking very, very like Ontario Public School here always says rise over run. Maybe in the rest of the world we don't, but it's delta y over delta x. Math is a universal language. Hopefully everybody knows what I'm talking about here. So delta y, and then delta x is happening down here. Delta x would be 3,000 minus 1,000. So it's 2,000. So there we go. That's a nice place to measure it. But it's up to you, and it's up to the context of the problem where you would measure this. In real life, which we are not in right now, in real life, if you were to design a transformer, for example, then you would be designing the transformer for a certain current. That current would be giving you a certain H, and you would be trying to perform inside that H, let's say 2,000. And then you need to know what your permeability is, the slope right here at 2,000. So, it's an academic exercise which permeability slope we take when we're just learning about magnetism. But in the practical world, you would know where to take this slope. So I hope I've done a really good job of making a horrible looking diagram. I'm not going to draw on it anymore. I'm going to just point your attention to the fact that, like we just talked about steel, iron behaves the same way. It's just that it has like a shorter straight section, and then it has a different curved section, but then it gets maxed out on its magnetizing as well. And that's called magnetic saturation. And where you take that permeability is up to you based on the problem. Now let's look at this. All just describes it. Let's look at this kind of simplified now. Kind of simplified. Good point. If you had to find this is all just in general, if you had to find the permeability in order to do some basic, I'm just learning magnetism, mathematical calculations, for example, reluctance calculations. So for your reluctance calculations, it's directly related to permeability, and you're saying, whoa, what's the permeability? Then typically you're probably going to you're going to shortcut, and you're going to do a calculation of what is H. You're probably going to go H equals Fm over L, and Fm is N times I over L, and then that gives you H, and then you're probably going to go, all right, well, now I know H. This is now known. And then you're going to go up this curve. You don't invent this curve. This curve is known. This curve is known, and now you know this. And you're going to go over here, and you're going to say, oh, now I know flux density. And now this is actually a number, and this is a number. Permeability equals my known flux density over my known magnetic field strength that I calculated. Now I know permeability. Let's sub it into my equation. That's how this is going to work in your world. Or let me go through another way that this is going to work in the world of just learning magnetism. In the world of just learning magnetism, I'm going to repeat myself again here. You're regularly solving problems. So I'm going to repeat myself again here. In the world of learning magnetism, you are usually solving problems where you have to find reluctance. Reluctance is a function of permeability. You don't know your permeability, and it used to be a number, but now you know it actually relates to this BH curve. So if you don't know how to take the shortcut, you're probably going to go and you're going to calculate permeability I mean, you're going to calculate magnetic flux density, and that's going to be related to, that's going to be the calculation of the number of flux lines over the cross-sectional area. Then you're going to do a little bit of geometry in cross-sectional area here, and you're going to go through and you're going to get a number. And that's going to make you happy. What you're then going to do is you're going to look at the y-axis, and you're going to find that number. And you're going to say, oh, here it is. This is my flux density equals known. And then you're going to go over on this axis. And then you're going to go down on this axis to find H. Now, H is known. Now, this is a number. This is a number. And you're going to say permeability, which used to be just easy. Now it changes. Permeability is my flux density, which is a number, and my H that I just pulled off the chart as a number, and it is now known. And I can continue because now I can put this in my equation. That's how you're going to use this. Moving on. Next topic. Just so you know, you're never going to have to know this, except for when you're learning magnetism, is that there's actually on this curve, which is, you know, material property. You can't change how steel works. Anyway, when it first starts to sort of, when it kind of starts to curve here, this is called the lower knee, and this is called the upper knee. And once it starts flattening out, this is called saturation zone. And there's a whole bunch of curves that you can take there. So let's look at the curves that we can take there. I believe I have it down here. And we can calculate the permeability quite a few ways. Normal permeability, incremental permeability, differential permeability, and average permeability. Again, this is not going to transfer into your electric machines or your transformers course, but these are options for how you can take the permeability off this curve. You can take the average permeability if you draw a straight line from the origin to the upper knee. You can take the differential permeability is very representative if AC current is flowing. That means that that this is constantly changing, therefore this is constantly changing. So the differential permeability is you're always taking the differential, you know, the derivative of the curve, and it's the derivative of the curve as you go along. Incremental is taking like a viewpoint in time of that differential permeability, and it's like letting you choose a change in flux density over a change in permeability. I mean, a change in flux density over a change in magnetic field strength. And the normal permeability is just B over H. This would again go from the y-axis, or sorry, from the 0, 0 axis. So if I look on these curves, I could draw these different types of permeability. I'm looking at this cast iron curve here. It would be called like a average permeability. If I go from this axis, I go from 0, 0 to this, then that would be average. I could take a differential permeability, which means I'm differentiating as these change. So that would be d flux density by dH, differential permeability. I could take a delta permeability, by taking two lines and taking the rise and the run of those. Rise and run would give me delta permeability. Delta rise over delta run is a type of permeability I could take there, or I could take the overall permeability, which again comes from the zero axis, and we just call that permeability. And that's just beta over H. So lots of different ways you could take that permeability. I'm glossing over it because it's not entirely practical, because I know that in the real world, you're going to be designing a transformer and you're going to be designing it for a certain current. Transformers are chosen for a certain current, or if you're the designer, you're designing it for a certain current. Taking into account the inrush current of magnetizing that core in the first place gets complicated. All I need you to know right now is that permeability relates to magnetic field strength and the flux density. And it differs as you change that current because it's changing the magnetic field strength. So this x-axis and this y-axis are interrelated, but thank goodness they do represent themselves on some curves. So if you can calculate your x-axis or you calculate your y-axis, then you can go across and find each other and then put the y-axis on top of the x-axis and find the slope at that point and call it the permeability that you are so happy to take and put in your calculations. Best of luck if you have a magnetic circuit calculation that is made out of a bit of cast steel and a bit of cast iron and a bit of laminations, and also has some gaps in there, because that's a whole lot of permeabilities to calculate. And now that they're nonlinear and they're represented by the magnetic, by this BH curve, that's a whole lot of finding X values or Y values and calculating the slopes just to go and put in those equations.